दो तीन मिनट में मेरा स्टार्ट होगा थोड़ा तो बोलिए कुछ सुनाई नहीं देगा नहीं वीडियो ऑन करने वाला मुझे सर्टिफिकेट नहीं मिलेगा एनपीटीएल का लाइव सेशन एक्चुअली अभी स्टार्ट होगा हाँ ठीक है बस थोड़ा सा धीरे रिकॉर्ड एक्चुअली होके वो यूट्यूब पे अपलोड होता है ना तो इसलिए तो कौन करेगा हाँ ସେଇ ଆପଣଙ୍କର ଯୋଉ କୋର୍ସ ଟା ନାଇଁ ତାର ଆକ୍ଚୁअली 2 ଘଣ୍ଟାର ଲାଇଭ ସେशन ହବ ଏବେ ସେଇ ଯୋଉଟା ଓଭରଭ୍ୟୁ ଗୋଟେ କରିକି କ୍वेश्चंस କିଛି डिस्कस କରିକି ତାଙ୍କ डाउट्स ନବାର ଥାଏ ତ ଟିକେ ଟିକେ ତାଙ୍କର ଆପଣଙ୍କର ତ ଠିକ ଅଛି ସେ ଆକ୍ଚୁअली यूट्यूब ରେ अपलोड ହେଇକି ସେଟା ଆଉଥରେ ସେମାନେ वेरीफाई କରୁଛନ୍ତି ତ ଆଇଟି ମଧ୍ୟ ଆସିଲା ठीक है मैम हेलो हेलो आई एम ऑडिबल राइट हेलो गुड इवनिंग एवरीवन So I think today we'll start the session. So just for 1 second, if anyone can confirm that it's my voice is audible. Okay. Hello. Okay. Hello. I think now we'll start. It's time. So it is audible now, right? Okay. Okay. Thank you. Thank you for confirming. So today we'll discuss about the week 2 overview. Basically what we did last time. So we'll see the content of this week 2 followed by Q&A session and the doubts. So I think last time some of you were asking for the contact. So this is my email ID, my LinkedIn ID if you want to connect. These slides are also available in the Google Drive. You can access, and the video recording of the meeting is also available on YouTube, so you can access those also. Slides I have already uploaded for week 1, and for week 2 I'll upload after today's session. Okay. So this week you started with SCADA, right? So first I would like to hear from any one of you, and then we will go through it one by one. So anyone, if you want to speak for something, what you understood from the SCADA. Uh, I am audible, right? I would like some of you to speak, otherwise it will be just like as if I'm speaking to the screen. Thank you. Okay, so we'll go one by one. So the SCADA will collect some data according to you, right? So why we need to collect this data? Okay, yeah. So this remote terminal. Why do we want to do this remotely? Why not on location or something like that? So I think okay. Yes, Anupam sir, you can speak. Yes, right. So basically what we want is we want to monitor a large amount of devices which are spread across a area. Okay. And we want to do that by sitting in just one room, that is our master station. And from that, we want to control the devices which are spread out over a large area. So for that, what we do, we first have sensors at the on-site location. So these sensors, they will collect, basically detect the data over there, and using the communication system, these information regarding what is actually happening in the on-site is transmitted to the master station. And the master station, it is like a control room. It is the control decisions will be taken here. So depending on the data, it will now perform some calculations or some control algorithms or something, and then it will decide that what action should I take if my the state of the system is something, let's say XYZ. So what action is if required, then it communicates it to the RTUs, and the RTUs, they then perform those control actions actually on the on-site location. So, and for all these, we need the communication system. So basically, as we see, the three main players here are the master station, then the remote terminal units, and then for communicating between everyone, we need a good communication system. So what are the components present here in the master station? We have first a data acquisition server. So what it will do, it will collect the data. Basically, first step you have to know is you have to know what is the system, what is happening right now. So for that we have the data acquisition. It will acquire the data. Then we have a real-time data server. What it will do, it will save the Okay. Huh. It will save the real-time data in the real-time data server, and we can let's say it will store the information regarding the voltage, current, frequency, and all those in the real-time data server. Moving on, then we have historical data server. So let's say we want to store data of 1 week, 1 month, or maybe 1 year, and we want to study the data because by studying the data only we can know what is the need of the system. Let's say over 1 month or a period of months, we have the data regarding the load, the line flows, and from that we can see if the or the power lines, they have their power flow close to their maximum limit. So that is an indication that the system is congested. So we have to build additional infrastructure. So for all to carry out all those calculations, we need data, and that will be stored in the historical data server. Depending on its storage, we can store about the period of time, whatever is required for us. Then we have an application server. So what happened is, right, we have the data, but we don't know what to do with it, with that data we have collected. So that will be decided by the application server. It will perform some studies, power system studies, basically maybe stability studies, maybe some power flow studies, and then it will come up with some control actions. Control actions. So for that, I would like to ask a question here. Considering our power system, can anyone tell me what are the parameters which are available with us to control the system? Like how we can control the system? Hmm. Hmm. Yeah, that I am agreeing with you. But first, in control system or something, you must be having the knowledge about system state and system control. So first we will have to identify the system states. So for power system, which attributes are the representing the system state? Yes. Yeah, so basically voltage magnitude and angle, and the voltage angle will reflect on the frequency. It is linked to that. And voltage magnitude, so two states we have: voltage magnitude, voltage angle. Then let's say to control this voltage magnitude and voltage angle, what all can we vary in the system? What all things we have? Circuit breaker, you can't control the power. It is part of the protection device. So what will these reactors or capacitor banks basically do? Uh, how they do that? How they will increase the voltage? Yeah. So one. Hmm. Okay, you are right. So whenever there is a frequency mismatch, we have to feed in or feed out power. So can we specify what power is that in case of frequency? What we need to do in terms of power? Active power. So and for voltage magnitude, as you all said, it will be controlled in the form of reactive power. So these inductors or capacitors, basically they vary only the reactive part. either they will capacitor will inject the reactive power or reactor will absorb the reactive power. They can't play with the active power. And in case of frequency mismatch, we have to vary the active power. So active power will be done by our generators if we have like that group governor system, so from that or from storage devices. So that is a different thing, that where from it will flow, but we have to control the active power. So basically our control parameters will be then active and reactive power flow. Okay. So these all calculations, basically the application server will decide. It will get the state of the system through the sensor, that is the data of voltage, magnitude, and angle, and then it will calculate something, and it will calculate that whether it has to feed in active power, take out reactive power, and from where also, that is also a question. So all those calculations will be carried out in the application server. And then we have the operator at the workstation, which is interacting through a HMI. You must have read in the course, which is a human machine interface. Basically, in the machine, it will see the state of the system, and then it will interact through that interface and send the control signal to the on-site location through the help of RTUs. Basically, that action. Then, basically, as we saw, just a second, I'll take the So basically we have the field devices in the field remotely spread out over a large geographical area. And from that, we collect the data and transmit it through the communication system to the data acquisition server. Basically, all the data is stored here, and then it will classify. The real-time data is stored in the real-time data server, and all the data accumulated over a period of time, they are stored in the historical data server. And then the application server, using those data, it will take the decision of the control variables. So that calculation will be done in the application server. And then we have operators at the workstation who will then communicate with the help of HMI, and they will give it back to the RTUs, and RTUs will again take the machine control action real in on the on field. So then again, coming to RTU. So we have talked about this RTU in detail. So can anyone just quickly regarding RTU? Okay, basically as we can see here, the RTU, it is again having five types of, we can segregate the one that is done in RTU. Firstly, we have a central RTU where all the data will be there. Then there is some physical input output ports through which the communication will take place. Then data collection application, basically it will collect the data we have seen. Then this data processing application, which is similar to the, as I told, application server part, where all the data processing will take and we'll know the control action. Then one thing that is new here is data translation application. So would anyone like to speak about this data translation application? Why we need this? Yeah, correctly. So first one is for the data collected may have some different unit, and so for all those conversion data format, maybe some degree Celsius, as we know, the unit from degree Celsius to degree Fahrenheit conversions, those unit conversion or data format like from ASCII or hexadecimal conversions. So all those conversions is done in the data translation application. Then we may also require data compression or data filtering, because we are having so much large bandwidth of data here. So maybe to accommodate that amount of huge data, we need to compress those data or filter out some unwanted data, so that also is done in the data translation application. And finally, calibrate the data, which we talked last time, that GPS, global position clock, and how we calibrate the PMUs so they have a unique reference, or we can say one reference with the respect to the global clock. So that function calibration and scaling, that is also done in the RTO. So this is the architecture, overall architecture you can see. So firstly, we have the field equipment here, and then through the input ports, digital and analog input ports, it will interact with the physical input output application, and we get the data. Then after that, what will happen? We'll also have some intelligent electronic devices. They will also communicate the data, and we have now collected the data from the field equipment, also from other intelligent electronic devices. And after that, what you can do, if needed, we can perform the data translation if needed. So after data translation, what we'll do, so the data processing will communicate it to the master station, and the master station will again communicate back what it has to do, what action you have to take. That will then be communicated to the field equipment to the data, to the output ports of the RTO. Okay, so this is final, we can say, of the three systems we have. That is master station, RTO, and obviously communication between them, which is present here. So firstly, input ports and this pulse accumulator. Does anyone have idea why we are having this pulse accumulator? Some like PQ, as you told, no? PQ. So basically, the RTUs is physically connected to some, we say actuators, we say in the hardware part. So depending on that, it will communicate it that to those hardware devices. So basically, that function. Change of data rate. Uh, I'm not sure whether that function can be carried out. So you want to say that whether that resolution of data is not sufficient, and if the master station is requiring more amount of data. Mm-hmm. Okay, that I'm not sure of. I can look up for you and tell you in the next session maybe. Okay, I'll just note it down once again. Okay, you just want to say whether it is in terms of hardware always or any software changing also we can do. Okay, okay, I'll certainly tell you in the next session. So we were discussing about this RTU. So we took the in. Okay, sure. Hmm. That may also happen, or that is uh, when it is measuring some energy or load, we say. So basically, as we have seen, it will, or maybe load or maybe generation, anything. It collects the data in the form of pulses. So it will count the number of pulses over a period of time, as you said, over 5 minutes, and then it will count those pulses and it will calculate the equivalent load or generation, what is that, and it will pass on to the master station. So it is what you had said only. So for that we have the pulse accumulator. So basically then we have the data from all these three input ports, and from that it will pass through this data acquisition server here, and it will communicate it to the master station. Then the master station through the application server, it will uh, perform the energy management control decisions, and it will give those decisions back to the RTU, and then RTU is having some output ports, and through those output ports it will control those devices in the field location. Okay. Then after that from SCADA, I think what you studied next was a functional diagram of a smart meter. So this, I think, if anyone can summarize for me, it is quite straightforward. Basically, what we do here is signal acquisition. So acquisition means we know we are acquiring further signals. Then we have to condition those signals. Maybe some filtering we may require, similar to the pre-processing, we may say. That is the equivalent term for conditioning here. And then we'll convert those A to D, ADC conversion here, analog to digital, and then we'll compute, let's say, the total energy if it is measuring, or the power factor, whatever. So those computations will be there, and it will be communicated to the users of the smart meter. After that, we'll move to the different types of distributed energy resources. So here we are basically talking about the distributed energy resources that are connected in the distribution side of the system, but not in the large scale ones which are connected to the transmission side. So for that we are having first one, the large most that is solar PV systems. Then some small scale wind turbines also may be there, small scale biomass systems, then this combined heat to power systems, energy storage systems in the form of, let's say, pumped or battery hydrogen energy storage. Then we have hydro systems, basically small hydro turbines. Then we are also having fuel cells. Then we have EVs, or plug-in electric vehicles. And demand response, although they are not generations, but they can regulate their response, and it may show appear that they are flexible generations in the system. So demand response programs, that is a special one. Okay. Supercapacitor, they will come under energy storage systems basically. Yeah, under the energy storage systems, you can tell them. Here you can, as I told, here you have pumped hydro storage also. No, right now. No, I have not seen on field right now supercapacitor. Diesel gen. Okay, so supercapacitors, they will basically store energy, and for storing again, from where it will store the energy, that will also. So standalone you can't do that. You have to have some other sources with it. Let's say some PV or something. From that you can, it will extract the excess amount of energy and store. then only it may discharge. But these supercapacitors, they can't generate any energy storage systems. Basically, what they do, they will extract some form of energy and they will store it. But they are not so widespread in use. Those functions that you have told, basically you won't do it manually, no. So you have to have some control system feed it into these programs in the form of, let's say, microprocessors or something. So those control things you have to have, and that is basically the, so you will use the supercapacitors in the place of those. Basically, we are having now water batteries in the home with the inverters. So are you suggesting that? Okay. So I am not. See, these are, I just can't say hardly yes or no because you have to study many of its aspect. Only we can vaguely just say, okay, it will discharge like that and go. But then you have to also perform its dynamic studies also. We are just now looking about how it is operating, or we can say the steady state conditions. But before that, we have to also perform the dynamic studies of these, and I'm not sure if those studies have been carried out for these devices as of now. So basically, it's that thing. I know I have also not seen. Okay. So, so that is the thing. Just I can't say yes or no because anything which will be deployed, we have to do thousands of other studies, not just one type of study. So, from looking now, I think it is easy to say that yes, it is doing the same kind of function, but the energy storage, as you know, the battery, the chemical energy process which is going inside the battery, that is different from what is with a capacitor. So, those type of studies also have to be carried out, and I'm not sure about those kind of studies basically, if they have been carried out for the supercapacitors or not. Okay. Uh, so this, yeah, that what you're telling about. So those storage system, as of my knowledge, those have been in the form of lithium-ion batteries only. And right now, what is upcoming is hydrogen energy storage systems, if you are aware. And our country is also pushing to this to move to this green hydrogen. Basically, hydrogen, we have two types of hydrogen, which is gray hydrogen and green hydrogen. So gray hydrogen, we are abundantly, that is found, which is formed in the process of the steel manufacturing and other industries. So that we don't want to use. What we want to do is green hydrogen will be produced when we do the electrolysis of water. And for the electrolysis of water, we have to have electricity. That electricity will take from the renewables, from the solar, let's say. And using that electricity, we'll do the electrolysis of water, and those byproducts we'll get is hydrogen. So that is the green hydrogen for which the nation is pushing for. And and this then hydrogen is basically, I think, stored in the form of ammonia tanks. So this ammonia tanks, it is there, and when needed, again the reverse reaction is done so that we generate electricity. So as of now, I have known about lithium-ion batteries for energy system storage. I know about hydrogen energy storage, and pumped hydro. It is a different one concept also. It is also for pumped hydro storage. We have two reservoirs basically, lower head and upper head, and they pump the water in cycle according to the demand management. So these all I am aware of. Why? Uh-huh. So what you are telling that is cost, basically cost benefit analysis what you have to do. So what the problem of peak management is that to meet the peak amount of load for a short period of time, we are having to invest more. So that is not viable. So for that, these distributed energy resources are helping because we don't have large infrastructure costs involved with them. So this cost. Hmm. So this cost benefit analysis, what you have to do. So this pumping back, what you are saying, the amount of cost that or that is involved, and plus the infrastructure cost that is you have to do for building the small micro hydro plants or DGs. So over a period of time, so the only the cost benefit analysis can tell us which one is more viable. Okay. See, many stakeholders are available already. See, pumped a hydro store. Hmm. I am not. What analysis? That, oh, obviously, if someone is doing or the government is opening, like the government DST opens up some projects. So under that, if needed, they open up projects and they offer us, and by that way, those studies are basically carried out. So it may so happen that what option you are telling us that may have already been taken care of. Maybe I am not aware of, or we are not aware of. So basically, our industry is evolving. So that is the thing I can tell you. Um, so this benefits of DRs. So there are many benefits. We'll talk about those one by one. So starting from enhanced grid resilience. So anyone would like to add a point here? So basically, what happened earlier is, in case of partial or complete blackout, we waited for the large these generators, thermal generators to start. So without that, since we have generations within our, let's say, locality, so by that way, in case of blackout, we can start those readily without the help of other thermal generators, and by that way, we can help in grid resiliency. Then moving on, it is reduced energy losses. So can anyone tell why we'll have lower energy loss if we use DRs? That is one thing, but cascaded tripping will not happen. That is very. like what to say, we can't assert that statement, but one thing is that we can have islanded mode of operation, since we have power within a closed locality, so that locality we may form a small island or microgrid what we say, and we can operate, and as the grid is formed we can connect that islanded microgrid back to the grid. So the next point is reduced energy losses. So anyone want to say why? So since we don't have to yes, anyone wanted to speak? Okay, since we don't have to like the transmit the power. Earlier, what would to happen if you want power at your home? Maybe it will be from a generator which is located far from you. So while transmitting that power, some amount of loss is bound to happen. So that can be avoided if at your home you have some PV and you are using it in the remotely, then that amount of losses can be avoided by with the help of this distributed energy resources. Then obviously thirdly we have a sustainable energy mix which is consisting of these green resources. Then for peak load management. So can anyone tell me what is this peak load management? With the that is one thing, or we can one thing we said about pumped energy storage, or that is with the help of demand response activities, we may flatten this load curve. Then flexibility in terms of what? To so that is not only limited to the cold start or hot start, also ramp up as we know. Let's say a thermal power plant is working with 10 megawatt capacity. To ramp up to 20 megawatt capacity, maybe it will take some minutes or hours. But if you have distributed energy resources, they can ramp up in you know at a very higher rate. Within minutes, it can ramp up. Maybe hydro or this inverter based resources, they can ramp up in basically less than a couple of minutes. So that is we have flexibility as so basically to match the generation with the demand. So we can say instantaneously we can have this flexibility from the DERs. True. Ah, it's solar. If you want to control, you have to always have a storage with it because you don't have a control with only a PV. It will depend only on solar irradiance. So basically, whenever we have a PV to control it, we will have to. Huh. Yeah, that was what I was telling to him. That only if you have standalone PVs, you can't control. So basically, whenever we have a PV, we have a storage coupled with it so that we can control the PV. We can say whenever you have access. Hmm. Then we have a voltage and frequency regulation. So basically, what we talked initially, for that voltage magnitude, we have to control the reactive power, and for frequency, we have to control the active power. And since these resources, they are for voltage also, we know that we have to feed it locally. So basically, if you have these resources in the remote end, it will help in having a better voltage profile. And ancillary services, basically, these ancillary service refers to those amount of service which is required for the system operations, we can say, in the real time management of the system operation. So these ancillary services may be for frequency, maybe for voltage, maybe for let's say balancing of load and demand, sorry, generation and demand, or sometimes black start ancillary service also comes under a type of ancillary service. Then we have grid. No, so that is different to the ancillary service. What you're talking about is, let's say, for operating that power, you need like offices will be there or batteries will be there. For that running of those systems, so what you are trying to say is for that system. But ancillary services is different. This services is required by the power system in the real time, so that uh, for a short period of time, we have to take care of this voltages and frequency, and from let's say this 15-minute time window to have this voltage support or frequency support. So this type of services can be provided by the DERs. Okay. Okay, then moving to grid decentralization. What example, which context actually I'm not getting? Example for what? Sorry. Yeah, ancillary service, like for, as I said, there are three, four types of ancillary service that may be for frequency regulation, maybe for voltage ancillary service. Then it also maybe black start is also one type of ancillary service for congestion, for the line flow congestion management. That is also a type of ancillary service. Basically, to have a optimal system operation, the P or Q that is required by the system, which can be provided by the DERs, those will come under the ancillary service. Let's say the line is congested now in the system. So what we want is either the generation to, and you can go for this in the POSOCO side under ancillary service. You have this frequency, rightly this is frequency regulation and voltage regulation, and this PQ that they are acquiring, they are required for the ancillary service. So for frequency, we have for a shorter duration, then voltage is for next duration of time, and black start is a different one. It is over a period of time. Okay, so grid decentralization, I think we talked about in the previous session also. So after that, we have infrastructure cost, basically for this peak load management as we talked. So to meet the system peak load, we have to build additional infrastructures, and those can be avoided if we have the distributed energy resources with us. And obviously, energy independence and environmental benefits due to this clean energy resources. Then I think next, what you were taught is about the PV solar generation. So first we need to discuss that why we are going for silicon as a material for solar cell, why not other materials. The earth, yeah, that is one of the reasons silicon is abundantly available with us. Then basically over the time, so the research, as we can say, the technology has, as rightly said, it has matured over a period of time, and we have reached to higher efficient silicon PV solar cells. And so this basically technology reliability and stability has also been studied, and we have large scale factories. So the scalability we can scalability required for this solar PV, that is also being there. And then obviously environmental compatibility. Can you tell me what it is meaning? We are not basically replacing, but we'll see in the next slide the first, second, and third generation of solar technology that we are going. So that is our, I think, very next slide. So just two slides more. We'll discuss about that. So apart from that, we have some disadvantages of using this solar PV energy resources. So as we can see here, firstly, what it is, initial cost of deploying these PV panels, it is high, but once it has been installed, the cost involved is quite low. Then obviously they are intermittent energy source, as we know, we can't control it. It will vary as with the solar irradiance. So for that, we need to have storage devices installed with them. So that will add on to the cost of the solar PV. Then coming up, it will require obviously space for installing these PV modules and storage. Then coming to grid integration challenges. So basically, since they are not controlled, so in the time of high generations, we are feeding in more amount of power, which is leading to voltage issues in the grid. So that challenge is there. Yes, anyone wants to speak? Okay, okay. So basic. So space requirement for rooftop PV, you can say they are some kilowatt scale capacity. But that again, it may be of less cost, but some amount of cost is always involved. So for that, I think we are also now going for floating solar parks. So we are installing this over the sea. So, but that maybe it may be negligible, but that land cost has always to be there. And for storage also, not in use, but it will all. Let's say you have a land which where you don't have, do any farming, and you have just an asset with a it is just an asset to you, and let's say the government has identified it as a good location for installing the solar. So obviously government will pay something as a remuneration to you. It can't just take away the land from you. So those lands, maybe the desert, so some amount of cost is always involved there. Okay, then we have this recycling and disposal. Basically, this problem is coming up now because the life of the solar PV was basically some 30-35 years, and that stage we have not reached till now. It is like we are approaching to that. No, the first generation, I think it is up to 20 years. And so for that only, we have not faced those issue now till now because we have not reached up to that stage. But as we are approaching to that, this is a problem that is upcoming, the disposable of those solar PV panels. And then again, we have how to then recycle this panels to again reuse maybe. And obviously geographic limitations. Not every land is viable for installing PVs. Only land which are having high rich in solar energy, those only can be used. Then coming on to this, okay, technology, PV technology, first generation, second generation, and third generation. So in the first generation of silicon, we had crystalline silicon, which is basically monocrystalline or polycrystalline, and it has a high efficiency, 13 to 22%. You can see by far the most efficient ones. But first, I think they were the production cost, manufacturing cost of this first generation was bit higher. So we moved to the second generation to reduce this manufacturing cost. So we moved to this thin film perovskite or cadmium tellurium materials or this amorphous silicon. So what we have achieved is lower cost of manufacturing, but the efficiency is still less than the first generation. You can say 10 to 20% of efficiency compared to 13 to 22% for the first generation. Then we have the third generation where we have this uh, we want this is basically third generation is completely in research and development stages. So we want to have both higher efficiency and lower production cost. So what we have right now is first generation of solar cells that you are having at your rooftops, and for second generation these thin film materials is used in solar parks or this maybe say calculators, this watch. So these kinds of application for the second generation of solar cell. And third generation is there. I don't think it has been deployed or used. It is basically in the research state in the third generation. So we have two types of this PV solar system. We can have as grid connected or we can have standalone systems. So in grid connected solar system, as we know, we take input power from the PV arrays, and then this DC power we'll have DC to AC conversion here in the inverters, and obviously then either if we can consume it, we'll give it to the loads, or if we have an excess, we'll give it to the utility. So if it is a grid connected one, so you don't necessarily need a battery here if you don't want to like exploit benefits. Without a battery also the system will work, but in standalone PV systems a battery is a must because don't have a grid to stabilize for you. So what you have a PV array and a battery and charge controller system. So and this again at the time of let's say high generation will store the power and discharge it when we don't have power. So directly if you have DC load we can give to DC, or you can feed the AC load through the inverter system. DC loads are DC loads basically true. DC loads only I think it when you have this hydro plants, if some battery charging is happening, then only we'll have. Otherwise, DC loads are not. Okay, so yes, previously we were discussing that we have a battery. So why this charge controller is required? We'll see with the battery. So anyone would like to say anything? Why do we need a charge controller with a battery? Basically, for the health of the battery, we need this charge controllers. So this battery has some efficiency, we say minimum and maximum levels. So for that, we have need to have this battery protection. We need to have a solar controller, and for the battery over, huh? Because hmm, solar. Hmm. But as you as a consumer, if you have a rooftop solar, are you concerned how much power you're feeding into the grid or taking? So you can have it, but it will be uncontrolled operation. It will not be an optimal operation, but this operation can happen. So, that is true what you're telling, but no, see that what obviously that is not a desirable or optimal operation, but this operation, can it happen or can it not happen? That is what is the question. So obviously this can happen, no? Although so, I would maybe we can go for a survey. Those who all have having a PV systems in their rooftop, so are they always going for battery storage within their premises or not? I think most of them don't do that. Okay. So this battery protection we have to protect the health of the battery, over current and overcharging of protection of the batteries. Then so will that see that will depend. I can't say very vaguely. It will depend on many of its, like how frequently its charging and discharging was happening, or we can say how active it was. So that degradation of this lithium ion battery cell, that is around that maybe. Okay. So and when you don't have the grid for the load management, so as we have said, so to make the generation equal to the load, so that function will be. Again, we have to do that with the help of this charge controllers and this remote monitoring and control, obviously when we don't have a grid. So basically all these activities in the absence of grid for the standalone PV system that will be carried out by our solar charge controllers. Then I have not gone through the detailed equations, and this was the final equation for the solar photovoltaic arrays. So these equations are with you in the slides. Then we have the IV and PV curves for the different solar irradiance values. So we can see as the value of solar irradiance is increasing, we see 400, 600 to 800. As it is increasing in this direction, the output current is obviously increasing. So it is quite straightforward, but still, if anyone wants to speak, basically more irradiance means more energy, and obviously, when you have more solar energy with you, more number of this electron hole pairs that you have in the material that will increase, and that will lead to the increased output. Then we had the impact of temperature change on this IPV curves. So we have seen as the temperature is decreasing, the output is increasing. That is, we have a inverse relationship here. As the temperature is decreasing, we have a increased output. So, but can anyone say me why? For solar irradiance, it was quite straightforward. With increase in solar, obviously increase in output. But in case of temperature, we have an inverse relationship. So, any idea why it is so? Okay, so basically, the temperature coefficient for voltage and current that is negative means whenever there is an increase in temperature, there will be decrease in voltage and current. So basically, when the temperature is increasing, instead of electron hole pairs being created, it results in their recombination. And if they are recombining means we have less free electrons with us, and less free electrons will imply decrease in output. And also there will be increased thermal losses in the system. So due to all these factors, with the increase in temperature, we'll have a decrease in the solar output. What do you mean by ambient temperature? So true, like you see here, it is for same irradiance but at different temperature. But summer and winter we can't see likewise because there will be a factor of the solar also there. Okay, this data I think I had taken from Ministry of Power of the energy mix we have in the India here. So we can see from fossil fuel we are having 56.4%, and this non-fossil fuel or renewables we can say we have reached up to 43.6, and this data is for 30th June. So basically we are achieving towards the goal of 100% renewables, I think. So we can say more about of half and half, 50-50 we have for fossil and non-fossil fuel energy mix in our country. Then I think what we studied was about wind. So for wind, we have this wind energy as input to the wind turbine rotor. So basically what will happen, this wind energy will get converted to mechanical energy, and this mechanical energy, again we have a gearbox system. So basically we can see it is a transformer, same as transformer electrical, a gearbox is in a mechanical context. So the mechanical energy will be transmitted through gearbox, and we'll have a generator who will convert this mechanical energy to electrical energy. And then we have, since this output is a DC, we have a converter here. We'll see that in the next slide, what type of generator we'll be studying for this wind. We'll have a detailed discussion there. So this generator, then we have a DC to AC conversion here, and obviously we'll have to step out this AC and feed it to the grid. So this is what we were talking about, the types of generator which you are using for wind energy systems. So first one is a conventional induction type generator, as you can see here in type 1. And can we see that there is some PF control capacitors? So do we know what is this? True. So these are basically fixed speed, our conventional type induction generators with power factor control devices installed here. Then in the type 2 or second, okay, type 2 type of generator, we have a induction motor, but here we can control its slip. So by varying the rotor resistance, we are able to vary the slip of this induction generator. And so this is a variable slip machine. Then coming to type 3, we have a DFIG or doubly fed induction generator. So what we have, obviously these are the stator parts, and we feed this stator output back to the rotor through these conversion systems to control, basically to make this variable energy. This wind is not to provide a constant energy to the grid. So we have this conversion system. This was the DFIG system, and what happened in type 4 is the permanent magnet synchronous generator, or as we know as PMSG. So what we have is directly only we have this correction, or we can say uh, power correction. Instead of going back in a loop, we have directly a converter in between the machine and the grid. Right now it is, right now we will find DFIGs, but we are moving to this type 4 PMSG because in a long run what we'll see, these type of machines will be more robust. These type 3 machines, they are being used widely, but they are having some stability issues, and in wrong, but this type 4 is in research stage, but we can say that in long run this type 4 will be better than type 3, but mostly we are having DFIG. True, but all will be a very hard one. Maybe some can have type 2, type 1, but mostly we can say it is type 3. Okay, I think we'll then go to the Q&A sessions. So first question is open to everyone. So, installed capacity of solar power. Hello, true, true. Machine learning techniques to identify faults. Fault detection, see, that is a very different data driven techniques we are having for this power system studies. We can say for power flow studies also we are having for topology. For fault detection, I am not sure basically what specific technique what you want to hear from me. But if you may specify what is your need, maybe I can help. What you want to do, what kind of data. Hello. Hmm. So what I can so we are speaking industry, and that too very low, like it is not that much of accurate in the research, although we have advanced very much, but the type of techniques that is being currently used, that is not that much advanced. And when you are talking about application, we have like forecasting, we have operation studies, we have protection studies, and for all of them we have different kind of learning techniques. But if you want to know about specifically the method, what I am aware of that right now this machine learning techniques, the neural networks or something, so they have been used with some physics informed or graph informed. So these idea or technology of physics and graph, we are feeding or combining it with the neural networks to get better results. So what I'm aware of, this is the most recent, but in paper, in research. But if you want to go for industry, as sir said, forecasting, and that too not that much of like what we can say mature or high efficient techniques are being used. No, not for power flows, not for detection. But if you want to go through paper, this physics or graph informed neural networks are the talk of the year. Okay. What? Okay. 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 So, first question, the installed capacity of solar power in India till 2016. This is a factual question, so you may type the answers in the chat box. Okay, one C we have. Anyone else would like to attempt? You can answer in the chat box. D we have. Okay, I would like to say that the answer is A. Okay, this we discussed few slides back. Second generation solar cell. Thin film, we get 1, 2C. Anyone else? 1. Okay. Basically, from first generation to second generation, we went for lower manufacturing cost, and also we went for like different type of like the material, the manufacturing that we're getting. So they are more flexible, they are more lightweight. So these kind of advantages we got while we went from first generation to second generation. And the answer for this question is thin film. Okay, the next question. What was the conversion efficiency of polycrystalline solar cell? We got a 3A, 3B. Okay, so the current answer is 3B, 11 to 14%. Then we have a small numerical maybe. PV array has open circuit voltage VOC as 370 volt and short circuit current 28 ampere and maximum power of 8 kilowatts. Then what is the fill factor? If you don't have like calculators with you, then you just type what operation it is, like what multiplied with what and divided by what. So do we know the for? Okay, anyone else? But actually, it is the reverse of what you said, sir. It is basically the maximum power divided by the open circuit voltage multiplied by IAC. So basically, it will be 8 kilowatt divided by 317 to 28. And if we do that operation, I'll just cross verify 1 second. 370. So it is 0.7722. So what is the significance of series resistance in solar cell modeling? So as you know, in the solar cell modeling, you have a diode, you have a series resistance, you have a shunt resistance. So what is this series resistance representing in that cell model? We got a load resistance. Are you sure? We got a C. So it is actually C. It is top and rear contact resistance. Then a question on IV and PV characteristics. So with the increase in solar irradiance level, what will happen to the open circuit voltage and short circuit current? How will they vary? We are getting, sorry, I missed B, D. B means some are saying that IC will decrease. But we saw in the graphs, right? Both were increasing with the increase in solar irradiance. Then, which state produces maximum wind energy in India? Maharashtra, Tamil Nadu, Gujarat, Rajasthan. We are getting Gujarat, Tamil Nadu. Okay, so the right answer is Tamil Nadu. Then we have the type of generator that you are using in wind turbine. We are getting W-fed induction generator, another DFIG. None of the above, someone wants to say. I think we discussed it type 3 in type 3 generator. It was DFIGs. Then what is the relation of wind stream to velocity stream? we got square relationship. Means we got cube. Okay, it is cubic relationship. Again, what is the maximum efficiency that can be derived from a wind turbine? Did we get any answer, or I'm actually missing any? B, I'm getting B. Okay. Okay, that brings us to the end of Q&A session. So, anyone have a... Yeah, sure, sir. Yeah, sure. Mm-hmm. Mm-hmm. No. So, did you follow any like documents that is being provided by the Indian Energy Exchange? Hmm. What type means? What do you want to know? I am not sure. What do you mean by what type? Hmm. Like what type of bids they are doing? That you want to know? What type? Hmm. How they clear? So I am not like a what what I know what they bid is for that 15-minute time window they have to give two things, specify two things: the amount of power that they can provide, and the for the amount of duration that they can provide, and third, the price that they are expecting. So for this 15 minutes time window, let's say they will tell that the how much amount of power they can give and at what price they want. So what will happen is, let's say 10 producers have bidded in the market, and what we do, we arrange the bids in decreasing order. Let's say starting from 20 to 10. So what we will do, we will arrange the like, hello, price for the bidder for the generation one. So that price will be in decreasing order for the generation companies, and similarly those who want to consume, that is load, they will also want to tell that how much amount of power they want and what amount they are willing to pay. So for the load the price are increase in the increasing order. So basically, just a second, I think I will write. So let's say we have here power, and let's say this is lambda is price. So let's say we had five load generations, those who are bidding. So let's say first one said that it starting, let's say from 10, it wants a payment of 10, and let's say some amount of power that I don't want to like mix here. So this is first bidder. Then second bidder, obviously we are in decreasing quantity. So let's say some specific amount of power, some specific amount of power, some specific. Likewise, let's say we arrange the bits for, so this black one is for generators. Similarly, for the loads, we'll arrange the bits in increasing order. So what will happen is they will want to, let's say, consume the power, right? So let's say here you get a overlapping. So what will happen is this is for the demand. So if I do this, simplify this into, let's say, straight line instead of stair type function. So at this point, what will happen? The generation equal to demand. So, and this price, what you will get here in the y-axis, that is your MCP or market clearing price. So for that 15-minute time window, the result of the auction is that this will be the clearing price, and we'll match the lowest one to the highest likewise. So is this clear? But this type of huh, market clearing price. So this type of bid that I told here, so it is not for worldwide. For someone, they also like this type of bid that they offer, no, that differs from, let's say, market to market, or let's say from country to country. For Europe, it is different. For US, it is different. So that basically depends upon how their uh, grid is working or evolving. Okay. Okay. Do we have any more queries here? No, no, it is ahead of. No, 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 it cannot find. So there is a document for it that for this 15, for let's say for right now it is 9:40. Let's say for 1940 it is now. Let's say for this 20 to 2015, 8 to 8:15 window. So that market will be clearing like process will start before that. So I am not remembering the exact time blocks, but firstly, for some one block of time, they will invite the bids, and I think ahead before 30 minutes, the bid closing date, like gate closure is there. After that, no bidding can take place, and to run the market clearing algorithm also, it will take one block of time, and before I think 15 minutes time they will decide that what will be the market clearing result for 8 to 8:15 block. So I think I can give you the link. Huh? From where? Mm-hmm. Okay. Okay. So what you want to say is you want your power to be delivered some specific location, or that you want to bid for that price, you want to play around that price. Hmm. From where? Like what do you want to do? Like what? Okay, you want to bid as a load in the auction you want to. Okay, okay, I got your answer. So as of now, I got it. So basically this. Okay, first, I think as far as I remember, so stakeholders, those who can participate in the markets, there is a set of rules and regulations. So for that, first you need to be in that bracket. I think some power, amount of power, like power of one, I don't remember the number. So some set of regulations is that for to participate in the market, you need to have those specifications. If you have those specifications, then I remember you will get a license to bid in the market. And using that license, then you can play if you want. But before that, you need to see if you follow those rules and regulation to be a stakeholder in that auction, basically. So I yeah, yeah. Not someone. I think I'll give you some documents because I read it some time back. I don't remember exactly what were the specifications. So if you want, I will give that document, and from that maybe you can find to whom to contact to get that license. Okay, it's like a banking. What banking? Bombay Stock Exchange also likewise happens. So this is for energy exchange. So to be in a part of that market, you need to be certified, no? Some rules, regulations you need to follow, some minimum requirement you need to have. Okay. Okay, anyone else? If you want, okay. Maybe you may introduce yourself since we are having some 15 minutes. Like, what is your background? I like to know that. Why you are interested to take in this course. Okay. Okay. Good. Nice. Very nice to hear that from you, sir. And then, so were you related to this power sector earlier, or are you currently related to any power system? Okay. Oh, okay. So nice to hear from you, sir. Okay. Okay, okay, sir. Very nice from you. And anyone else? Discom of which state actually? I would like to know. So Tata Power, BECS. Okay. So what do you want to tell me? Uh, See, this course, as it will flow through, it will tell you about the recent trends and developments. But what exactly you want to know, I'm not getting. Okay, maybe also distribution automation. Am I right, sir? Maybe in your distribution system also, you may be facing that relays, which were earlier, I think, electromechanical type relays, as my knowledge goes. They are being shifted to change to digital relays, and we are like upgrading our system. And yeah, that is one of the lectures in the ahead. Also, cybersecurity we'll touch very briefly. So why that is important, we'll see it there. Because hmm, so not only in terms of, let's say, uh, the, what you said, sir, in terms of power, they may say that I injected or not injected. That may be a talk. But some may also would like to play with the grid stability. They may show in the data that as if it is a very alarming condition, the system is vulnerable, but in reality it may not be the case. So you take a wrong decision, control decision there, and basically you. True, true. Because we are seeing the. Yes, sir. True. Encrypted. Huh. Yeah, that thing will be there. There are like the as we'll be proceeding, we'll be more sure what should be the standards, because as we have seen today, the solar cell also, the third generation studies are going on. Wind turbine also, we are slowly realizing whether DFIG was better or we may go to PMSG, and this communication protocols. Hmm. Uh-huh. Actually, this is the way we have been instructed, and those kind of assignments, I think you have in the course where you have some deadline and you have to respond to those questions. Okay, okay, true, true. Uh, okay, okay. I'll surely communicate it to my like portal seniors because this is the way that. Mhm. Just to discuss. Okay. Okay, surely I'll take the suggestion and communicate it to my like portal members because this is the way that we were instructed. So maybe we can change. So if that is possible, I'll surely let you know. Okay. Hmm. Oh, you want to know about there is IE. You will have some government sites and there mm, you may go through those like they have some pre-published reports and documents on how they're functioning and all. So those websites, or you can go through the websites of like Ministry of Power, POSOCO, PGCIL, whatever is concerned to you, and there you'll find many good documents related to how we are transitioning from the conventional power system to smart grid. Okay, okay, surely I'll take the suggestion and for real time. Hmm. Hmm. Yeah, yeah. Okay. Yeah, you surely can mail to them and they can arrange for sessions by. See, I have been assigned a work, but if you as a student, okay, okay, uh-huh. Okay, sir, I'll surely try to do that. Okay. Ha 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 ha. Mm-hmm. Okay, sir. Okay. Okay, I think then we'll close today's session. So thank you everyone for joining.